So I told you this has some interesting twists to it. So the next one is that all of these 30 minus 27s, they're just 3. So that means they cancel with these 3's in the denominator. So that means our T5, our Taylor series, 5th degree Taylor polynomial for cube root of 30 is going to be, so we're going to have 3. And then this 3 is going to cancel with one of these 3's. So I'm going to have 1 over 3 squared. And then I'm going to have minus, here's 3 to the 2nd power, so it cancels 2 of these 3's. So we're going to have 3 to the 5th in the denominator. So it's going to be 2 over 3 to the 5th times 2 factorial. And then this term is going to be plus. My numerator is 10. My denominator, now I got 3 to the 3rd power, canceling with 3 to the 11th power, giving me 3 to the 8th power times 3 factorial. And then it's minus 80 over, so now I've got 4 3's canceling with these 15 3's. So the denominator I have 3 to the 11th power times 4 factorial, not forgetting the factorial this time. And then I have plus 880 over, now 5 3's cancel with 19 3's, and I get 3 to the 14th power times 5 factorial. So it actually simplifies out to something surprisingly simple, despite all the crazy stuff that it came from. And it has interesting patterns where, you know, the denominator is just 3 to the 2n minus 1. And the numerator and it has, you know, 0 factorial, 1 factorial, 2 factorial. So it's the denominator is 3 to the 2n minus 1 times n factorial. But the numerator is just hard to get a handle on, and yeah, it would be difficult to find an explicit formula for that. So we don't want to try and write a summation because we can't write this numerator as an expression. But we can calculate it, and that's what we, you know, that's sort of the point here. So if we look at what we get when we do all those things, you know, here's 3 plus 1/9 minus 2 over 3 to the 5th times 2 factorial. So I simplified some things like 3 squared is 9, 2 factorial is 2. I didn't want to write the factorials because it took too long. All right, and so, and we know what 3 factorial is 6, right? So why write that? So what I ended up with for that was, and you can see the concurrence right there. It's really good. So the 5th order Taylor polynomial is 3.107232628, and the actual, in quotes, cube root of 30 is 3.107232506. So you can see that it corresponds right up to there. That's 1, 2, 3, 4, 5, 6 decimal places. You know, that's 1/1,000,000th. I mean, it's in a way I was sort of surprised because 30 is very close to 27, so I expected the approximation to be very good. But especially with, you know, 5, we have 6 terms of the polynomial. But this actually is very good. We love to see that 10th decimal place, but 6 is pretty good. It's within 1/1,000,000th of the correct value. All right, so now I want to look at some other examples that are a little bit simpler. And again, these are things that pertain to what's going to be in your homework. Pretty much all of this is. So one of them is write a Maclaurin series for x cosine x. All right, so what I want to point out is you don't have to sit there and get, let's do f and f prime and f double prime and f triple prime, which is going to require me to do, you know, the product rule like 80 billion times. It's horrible. Take advantage of the fact that you already know that, and you're allowed to do this, okay? You already know that cosine x is 1 minus x squared over 2 factorial plus x fourth over 4 factorial minus x sixth over 6 factorial. We can take that as known at this point. All right, so if I have x cosine x, I just multiply everything by x. All right, so now I'm going to have x minus x cubed over 2 factorial plus x fifth over 4 factorial minus x seventh over 6 factorial plus etc. It'd be nice if I can write that in a summation notation. So it's sum from n equals 0 to infinity, negative 1 to the n to get the alternation, checking my first term is positive. It looks like my numerator is going to be x to the n plus 1, and my denominator is going to be 2n plus 1 factorial. Yeah, so that's pretty nice. All right, next one, we're going to find T3. So this is using that notation. T3 means the Taylor polynomial up to the cubic term. This is a very typical kind of AP question. They won't ask you to do 50 billion terms. They'll just ask you to do something fairly, straightforward like this. So I need to lay out, though, because I don't have any reference point for this, what's f of 1, what's f prime of 1, what's f double prime of 1, and what's f triple prime of 1, and I'm going to stop there because it's T3. All right, I might want to get a handle, like I need to know what these things are. I like to write the derivatives over here. So here's our function ln x, and then so our first derivative is 1 over x, but since I'm going to do the derivative, I want to write that as x to the negative 1, and then my second derivative is negative x to the negative 2, third derivative is 2x to the negative 3. All right, so f of 1 is ln of 1, so we know that's 0. F prime of 1 is 1 over 1, right? It's going from here, so that's 1. F double prime of 1 is going to be negative 1 over x squared, so that's negative 1 over 1 squared, so that's negative 1. And then F triple prime of 1 is 2 over 1 cubed, so that's just 2. So there's my coefficients. I need to get the CNs by dividing everything by the factorials. So I have 0 over 0 factorial, 1 over 1 factorial, negative 1 over 2 factorial, and 2 over 3 factorial. All right, what do these things equal? This is 0, this is 1, this is negative 1/2. 3 factorial is 6, so 2/6 is equal to 1/3. Then I got to remember my polynomial terms, x minus 1, because it's centered at 1, so x minus 1 to the 0, x minus 1 to the first power, x minus 1 to the second power, x minus 1 to the third power. All right, so then I can say that the ln of 1 is approximately equal to, so we're saying approximately equal to because we're using a polynomial, a finite polynomial instead of infinite series. It's equal to the infinite series in most cases. Well, that's the next topic, the final topic, in fact. But since I'm only using finitely many terms, ln of 1 is approximately equal to, so I have my first term is 0, my second term is x times x minus 1, so that's x minus 1. My next term is minus 1/2 x minus 1 squared. And my last term is plus 1/3 x minus 1 cubed. Now, the book problems ask you to, and that's it, by the way, right? That's your T3, centered x equals 1. Your book problems ask you to graph the Taylor polynomial and the function in the same window. That's actually quite instructive, so I've done it here. Here is my Taylor polynomial is right there. X minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1. You can't see the cubed, but it's there. And here's ln x. So those are my two graphs. So if you just look at them in this viewing window, they don't seem to correspond too much. But remember that the center of this is x equals 1. It's centered at x equals 1. And in fact, if I zoom in and really look at what's going on at x equals 1, that concordance is actually really good in an area around there, and that's only with the third order polynomial. So yeah, there you go. There's Taylor polynomials. They have a center point, and they line up along that center point. All right, and then you get to do homework. It's a light feast of homework, so really dig into these problems and have a ball.